This is section 19.6, and in this opportunity we are going to make the connection between the Gibbs free energy and cell potential, both that can be used to determine the spontaneity of a chemical reaction. The connection between these two is through an equation that relates the Gibbs free energy with the potential, and in this case we have that N is the number of electrons being transferred, so the importance of determining the oxidation reaction, how many electrons are involved there, the reduction reaction, how many electrons are involved there, the number of electrons being transferred between these two reactions have to be the same. Okay, so that's the number of electrons, and more specifically here we're going to be talking in terms of the number of moles of electrons being transferred between reactants in a redox reaction. F is a constant that has the value 96,485. That's the charge of 1 mole of electrons. And E here is the potential. If you are using standard reduction potentials, remember this is under standard conditions, then the delta G that you are calculating is the delta G standard. Okay? So just keep that in mind. So for example, if we have this cell, electrochemical cell, remember this is your anode, this is your cathode. So in the anode you have an oxidation reaction. However, since we are writing this in terms of potential, we want to calculate the potential, then it's a reduction reaction, right? So we write it as a reduction reaction. So zinc plus 2 electrons go to zinc solid, and copper 2 plus 2 electrons go to copper solid. Now the potentials of these two half reactions is, for the zinc this is equal to minus 0.76 volts, and for copper is plus 0.34. Remember, the more positive the potential is, that reaction is going to happen as a reduction. The other one, if the potential is lower, then it's going to happen as an oxidation. In this case we have 2 moles of electrons, so N in that reaction is going to be 2. Okay, and the potential, the cell potential, is going to be plus 0.34 minus 76, and this is equal to 1.10 volts. Now if we are calculating delta G for this reaction, then delta G, since we are using the standard potential, this is the standard Gibbs free energy, and it's going to be equal to minus, remember the equation is minus NFE, so minus 2, this is technically moles of electrons, times 96,485 coulombs per mole of electrons, times the voltage, which is 110. Okay, here moles of electrons cancel with moles of electrons, and we obtain here that delta G is equal to minus 2212 coulombs per volt. Now the good thing about this is that 1 coulomb times volts is equal to 1 joule. Therefore this is equal to minus 212,000 joules, and this is equal to minus 212 kilojoules. Okay, so the use of this equation is rather simple, but you need to determine the correct number of electrons being transferred. So this is where, if you have a different number of electrons for the anodic and for the cathodic reaction, then you have to multiply by the proper numbers so that you make those numbers of electrons equal, and that is the number that you're going to use in this equation. Okay, that will represent sort of your balanced equation. So since we have been using delta G related to K, the equilibrium constant, so determining the potential will also allow you to calculate the equilibrium constant. Remember, back in the when we were working with equilibrium, we could calculate K from delta G or delta G from K through this equation. Basically, what we're gonna do is make this portion of the equation equal to minus n if E. And if you manipulate that equation, then you end up with this expression. Okay, just in case, minus NEFE is equal to minus RT logarithm of K. So you cancel the negative signs here, and then basically you take this to this side and then end up with this equation. Okay, so one way in which you can calculate potential from the constant or the constant from the potential of that electrochemical cell. So how do we use that? So let's use the same equation, the same electrochemical cell. Okay, for this one, we already know that the cell potential is plus 110 volts. Okay, we have already calculated the delta G for this reaction, and delta G standard for this reaction was minus 212 kilojoules. Okay, so you can go from delta G directly to calculate that, or you can simply use the voltage. Okay, so since you have already used voltage to calculate since you have already used delta G to calculate K, so how about we use the potential to calculate the constant. So the potential, based on what the equation that we had before, okay, is equal to RT divided by NF logarithm of K. Okay, so therefore what we're gonna have here is RT logarithm of K equal to NFE. So logarithm of K is equal to NFE divided by RT. So K at the very end is going to be the exponential of the whole expression, NFE divided by RT. So all this becomes now is just plugging the numbers, right? We have already seen that for this particular reaction is the same cell that we had before. We have 2 electrons being transferred. Okay, since we are working at standard conditions, then the temperature is 298 Kelvin. F, the constant, is 96,485. And what else we have here? The potential, it's already here, plus 110. Right? So in this particular case, this value for R has to be, technically the top one is units of energy, because you end up with coulombs per volt, and that's equal to 1 joule. Sorry, 1 coulomb per volt is equal to 1 joule, so we have to use 8314 as the value for R in this equation. So K is going to be equal to E raised to the power of, well, before doing that, how about we calculate that term, the whole term first. So NFE over RT is equal to 2 times 96,485 times 1.10 volts divided by 8314 times 298. And this gives us 85.7. Okay, so this, everything cancels here. Right, so we end up with 85.7. So K is equal to E raised to the power of 85.7, and this is equal to 2 times 10 to the power of 37. Okay, so this is the value of K, and this is a really large value of K. So this is a reaction that is very, very favorable. All right. So here K is much larger than 1. Now in this reaction, we want to determine the standard potential of a redox process. We don't know what the redox process is, but we are transferring 1 mole of electrons, and we have a value for K that is equal to 230. Okay, so pretty much K, the equilibrium constant, is 230. N is equal to 1. Okay, we are working with the standard potential, that means standard conditions, so the temperature is going to be equal to 298 Kelvin. We have R equals 8314. Okay, so if the equation that we want to determine, we want to calculate the standard potential, that is equal to RT divided by NF logarithm of K. And this is standard potential. So that standard potential is going to be equal to our gas constant, 8314, times the temperature, 298 Kelvin, divided by the number of moles, which is 1, number of moles of electrons, more specifically, times the Faraday constant, 96,485, multiplied by the logarithm of K, which is 230. Okay, we end up with a potential for that redox process. What the redox process, again, it doesn't really matter, but we obtain plus 0.14 volts. So not much electricity, not much potential you can get out of that process. In a way, you can predict that because this is a constant that is larger than 1, but is not extremely high like in the previous case. So you are comparing a constant of 230 versus a constant that is 10 to the power of 37. So that's a huge constant. This is a large constant, but not so large. Anyway, the potential here for this particular cell is going to be 0.14. Okay? So the important thing to remember here is now that you have 3 quantities. You have the cell potential that you can get out of the standard reduction potentials. You have your standard delta G, and you have K. The relationship between delta G and K, we have already explored that when we were working with chemical equilibrium. But now we are working with electric potential for electrochemical cells, and there is a relationship between all these quantities here. And here in this triangle that I have, I just want you to realize that within all these 3 quantities, you can relate each pair of those quantities. So if all you want is to calculate delta G from E and vice versa, then you use this equation. Okay? And if the one that you are already familiar with is delta G equals minus RT logarithm of K. So you knew this one before. We are introducing this one now. And then if you combine these 2 equations, then you can relate the value of the equilibrium constant with the electrical potential for that cell without having to calculate delta G. So basically you just use whatever you need here. I want you to realize that these are just 2 equations. This is the combination of the other 2. Alright, so you don't really have to memorize 3 equations, just 2. And then you just focus your attention on delta G, because that's the common factor between those 2 equations. Okay, so that's one of the take-home messages that I want you to take from this presentation. And the other thing that I want you to remember is that if you are working under standard conditions, then that means if there are gases involved, they have to be at 1 atmosphere of pressure. The temperature has to be 298 Kelvin, and Q has to be equal to 1. Q equal to 1 pretty much means that the concentration is equal to 1 molar. Pressures 1 atmosphere, concentrations 1 molar. That's what Q equal to 1 means. And for any given spontaneous process, okay, remember, spontaneous process will have a delta G negative, which is right here. Okay, but what it means in terms of the other variables that you have here is that if delta G is negative and that's a spontaneous process, then that means that the electrical potential is positive and that the K is larger than 1. K larger than 1 means you are favoring the products and the reaction is moving in the forward direction. That's pretty much how you can relate all these three quantities and make the connection with spontaneity of a reaction. Of course, if this is for a spontaneous process, then what would you expect for a non-spontaneous process? A non-spontaneous process, then the electrical potential is going to be negative, delta G is positive, and K is less than 1. Okay, so that's pretty much how you can compare spontaneous processes and non-spontaneous processes from the point of view of electrical potential, delta G, and the equilibrium constant. Okay, important things to remember from this section. Well, there is a relationship between the cell potential and the Gibbs free energy for any given reaction. You can do that through this equation. Okay, if you don't use these symbols, okay, this is at any condition, and if you use the symbol, the degree symbol there, then it means standard conditions. Okay, very important to in order to be able to calculate delta G from electrical potentials, then you need to determine the number of electrons being transferred, and for that it's really important that you are able to determine the half reactions, how many electrons are transferred in each half reaction, and then balance that number of electrons. That n, the number of electrons that you use in that equation, is the balanced number of electrons that are transferred between the oxidation and the reduction reaction. Okay, as we saw before, positive values of electrical potentials are associated with spontaneous processes in pretty much the same way that negative values of delta G represent spontaneous processes. And if you want to calculate K from cell potential or cell potential from K, then we have this equation. Okay, so basically the only new equation that we have actually introduced in this section is delta G equals minus NFE, and then we make the connection that with the other equation for delta G and the equilibrium constant, so that we end up with this new equation. Okay.